All right, calc folks, back here with another what would hopefully be a quick video here in our study of vector valued functions, where I want to look at the length of a vector valued function. This is going to be followed up by one other video where this length of a vector valued function calculation is going to give us a means of developing what we call the arc length function, and I have that set of notes already prepared, and I'll follow this video up shortly with that. But I am trying to keep these videos a little bit more brief so that I can get them out to you a little bit more quickly, right, in putting all this together. But let me bring this over into a view. Here we are talking about the arc length of a vector valued function, and we know for a vector valued function in R sub n that it describes a path or curve in that n-dimensional space, either a regular path or curve in 2 or 3 dimensions, or a hyperpath or curve in 4 dimensions and beyond, right? And this curve will either have a length or hyperlength associated with it, right? And we have a way of calculating that scalar value for this length using our vector valued function. And that calculation is what we see down here below. If I bring that up into view, by definition, right, the length of a vector valued function, r bar of t, in our n-dimensional space over values of the parameter t in this closed interval from a to b, right, the length of that n-dimensional curve or path, right, over some interval of its parameter from a to b is given by this calculation seen down here. All right, where what we note we're calculating is a definite integral over that interval from a to b, where our integrand is a scalar value. It is a scalar value given here by this magnitude calculation, where we're taking the magnitude calculation for the value given by the first derivative, or the vector for the first derivative of our vector valued function r bar. We are taking the magnitude of r bar prime of t in our integrand here, and we are integrating that all with respect to our parameter t. All right, that integrand is going to build a scalar valued function describing that magnitude length at a given value of t along the curve of r bar of t. All right. We do take note, if you take a moment and just think about this value given by the magnitude of r bar of t, and relate that back to a little bit of motion in space. If this is position, if we're talking r bar of t is position along a curve, the magnitude of r bar prime of t is the magnitude of the velocity function. And what do we understand magnitude of the velocity function is? That is the concept of speed. So really what we are doing here is we are integrating the infinite speeds that occur at every single parameter of t along this position function over this interval of time from a to b. And all those infinite speeds over that interval of time from a to b is calculated using a limit of a Riemann summation, right? Which then will yield the distance traveled along that curve, or this arc length value. So just a little bit of understanding of this calculation, you are looking here at integrating across an infinite number of speed calculations, right? Every single speed in that interval from a to b is going to be calculated in the form of a limit of a Riemann summation, and that limit heads to infinity, which yields this definite integral calculation. And this does relate back to an idea that we had back in our understanding of motion here, right? Right. Again, I do highlight this idea that we are connecting back to motion in space to help us understand this calculation, and that we're really relying on speed in our calculation for this distance or this length. All right. We go on then to consider an example here. We might consider the arc length of the function r bar t equal to t comma t squared. This is a rather classical parabolic shape in the two-dimensional space, right? This vector valued function t comma t squared in 2 dimensions for values of t in this interval from 0 to 3. Let's consider calculating the length of that vector valued function starting at t equal to 0 and continuing up to t equal to 3. Right? What would be the length of this parabolic curve? If we were to sketch this, we would get a parabolic curve that flows from the origin to the location 3, 9 in space. Right? And would have our rather classical shape to it. Well, from the definition of arc length, right, I really should have in there r bar prime of t. Can I get out of there, right? And then thus the magnitude of that r bar, can I get out of that too? The magnitude of r bar prime of t then is going to be given by the square root of this vector's components squared. So 1 squared is summed and squared, right? Or squared and summed. So 1 squared is 1, 2t squared is 4t squared. We add those together and put them under a radical to calculate that magnitude. And thus the arc length in this case would be given by the integral from 0 to 3, the interval over which we're integrating. What would be then the magnitude description along this curve at any given value? The magnitude of r bar prime of t for any given location along this curve. And that is given by the square root of 1 plus 4t squared. Right? Now, how do we get through that integral calculation? We are going to have to go back and rely on some calculus 2 techniques. Right? Where we can either consider the technique of what? Trigonometric substitution, but we can also consider just a quick little rewrite on this also, and perhaps look into the integration tables. And in fact, that is what I do here. That quick little rewrite is going to actually have me factor a 4 out of it here. I'm going to take the 4 out as a square root of 4, which is going to be 2. That is brought out in front. In order to factor it out of these 2 terms, it does come out of this term rather directly, the second one, but the first one, we have to divide it out. So it becomes 1/4 in value, our first term. Right? Where if I go look in the integration tables, I do have in the integration tables an item that does fit this format seen here. Where the antiderivative for this format seen here given by the integration tables is this statement seen here. Not so clean. Where that 2 is a constant multiple pulled out in front, I can then consider evaluating this at the value of 3, which also itself is not very clean, right? And subtract from it its value at 0, which does clean up. When 0 goes in here, the whole thing zeroes out for the first term. And when 0 goes in here and here, this does become, oh, and I did miss that. So I can clean this up a little bit more. This is going to actually become 1/8, the ln of 1/2. And I missed that 1/8 coming through here. So actually this 2 down here then, that 1/8 could actually be factored out for the moment. I could write this over this inside my ln. So really what I have going inside the ln, if I factor out the 1/8 for a moment, I'd have this over this. Ignore the radical for just the moment. If I factor out the 1/8, I could write my ln combined into a quotient using a little, difference to quotient rule. That does clean up. That 1/2 could revert to the numerator as a product of 2, so that would become a 6, and that would reduce that 1/2 to just the value of 1. where then I can bring that 1/8 back into the logarithm as a radical, a power of 1/8. And the power of 1/8 is really just the 8th root of that value. So a little simplification of that result will lead me to this result seen here. And this is what the back of the book might state, or this might be the result that my math lab is looking for, folks. All right. It is going to require you to do some combining of our LNs here. What you can notice is what I did do. From this, I factored out the 8th. This then does combine into one logarithm across this difference with a quotient. That was that quotient I expressed. I couldn't write that like this then, right? With this disappearing, using my log rules, where then that dividing by a half is the same as multiplying by its reciprocal. So dividing by a half is the same as taking all this and multiplying by its reciprocal. And that is where I get the 6 plus the square root of 37 from. Right? That's where this result comes from. Right? Where then the 1/8 can be brought back into the logarithm from the constant multiple to become a power on this quantity. And this quantity raised to the 1/8 power is really just the 8th root of that quantity. So that is how that statement is simplifying. Can I get this all the way back to the beginning? Pretty darn close. Let's take that out of there. Put that there. We had this here, and we had this here. And all of this was actually outside the brackets. Is where we went back to. Okay. So that kind of describes how those two logarithms simplify themselves into this one logarithmic value. And that is what my math lab is going to be looking for, folks. All right. So again, that is a quick little video over arc length. As with distance calculations back in distance along the curve back in, or arc length calculations back in Calc 2, these are not always very nice integrations. That's the other thing to keep in mind, that when you set up this integral here, it may not always be a really nice integration. And there's a lot of cases we can really just set up and then have to consider approximating through other means. And that's where some of those other chapter 2 ideas come into play, where we look at trapezoidal rule, we look at, what were some of the other ones? Simpson's rule. We have some approximation techniques for this value. And if we have to just go back to Riemann summations to approximate what we might get out of this formulation, we may have to just do that also. A midpoint rule, or a left or right Riemann sum. All right, folks. Again, integrations for arc length are not always nice calculations. It's that whole radical of these components being squared that makes it really an ugly calculation. And they do have to kind of be tailored at times to work nicely by hand. So don't be able to expect just to set up any old problem and calculate it here. They do have to have some, they have to be doable in some regards. So a lot of what the book presents is doable. A lot of what I present to you is going to have to be hand doable, or rely on those techniques given. I don't think I'll really give you any where you're going to have to use approximation techniques. That could be a little unbearable with this problem at the moment, I do believe. So with that said, folks, I will stop there. We do have another video coming up very quickly over the arc length function. I'm going to go eat some dinner. I got some class from 7 to 9, and then my hope is to record that before I head to bed tonight. But I'm going to try to get this posted up as soon as I can for you folks, so that you can watch this before class. All right. Hopefully you see this before then, and I'll catch you next time.